So we started, like I talked about, the last chapter here, which is kinetics. And as we talked about last time, really kinetics sort of deals with the idea of sort of how fast, or I guess you could also talk about how slow a particular reaction takes place. Um, we don't talk a lot about thermodynamics in this class, or have talked a lot about thermodynamics, but you will in 200B. And when you talk about thermodynamics, as we sort of talked about at the end of last week, that really deals with, as you will learn, really the idea of sort of spontaneity and whether or not sort of reaction will take place. And again, it's a good thing to keep in mind as you perhaps go into 200B, that when you talk about a reaction being spontaneous, again, it does not necessarily mean that it occurs really, really fast. Sometimes we associate sort of, again, spontaneity with something occurring really, really fast. It just means that under those conditions, that reaction will take place. What we're really focusing in on in sort of this chapter is that aspect of it, really, sort of how fast, or again, how slow a reaction takes place. And that's really where the area of kinetics sort of comes into play. We talked about the idea that, we could really follow, sort of the reaction rate. And when we talk about a reaction rate, oftentimes what we're talking about is really how the concentration of a reactant or product is really changing with time. So it's some type of time aspect of it, which obviously is why it's referred to as a rate. So a lot of times what we do is we oftentimes will follow sort of the change in concentration of something over a period of time. If this is a reactant, as we sort of alluded to last week, we would expect that in most cases the reaction is heading from the reactant side to the product side, which means in most cases, if we're looking at a reactant, we should see the concentration of it start to decrease with time. And that's because as a reaction heads to the product side, you pretty much need to use up your reactants to make your product. So we need to use our reactants to make products. So we would expect our reactants to come down. We would also, on the same token there, expect the concentration of our products to start to rise with time. So usually, we can think about starting with like nothing on the product side. Really, everything's on the reactant side. And as the reaction proceeds from reactants to products, we should see that decrease in reactants, increase in sort of products. We saw a little bit of that, and we'll see it here again in just a second. But we saw a way that we sometimes represent that, which is sometimes referred to as the rate expression. But we usually will sort of assign, in terms of the rate of reactants, sort of a negative sign. And that negative sign sort of indicates that we're expecting their concentrations to come down. While we assign sort of our products really a positive sign, or it's sort of a positive change in concentration versus time. And that's because the overall rate really should end up being positive for a particular reaction. We also talked a little bit about a couple of different sort of types of rates, an average rate, which is a lot of times what we look at sort of from like the beginning of the reaction to the end of the reaction, the average sort of change in concentration over time. And then we also talked about, sort of the idea of an instantaneous rate, which is really for sort of a period of time, kind of a window of time, and how those concentrations are changing for that window. I think I did like the example of driving your car, sort of, on average maybe 70 miles an hour for your whole trip. But there were maybe pockets there, if you took like an instantaneous sort of window shot of how you were driving, maybe you were 60, maybe you're 80, maybe you're 75, so there's those sort of instantaneous sort of rates that average out as a whole when you think about the entire reaction. Lastly, we sort of talked about the idea that there's a very sort of simple way sometimes to follow how the concentration is changing with time, especially when you're dealing with reactions that pretty much have some type of colored solution. So either a reactant has some type of color, a product maybe has some type of color. And in that case, you could use something as simple as like that experiment we did, where we used something like a spec 20 spectrophotometry. And basically you could follow the change in absorbance value over time. Remember that barely the absorbance value of a solution that has color is related to its concentration. And typically the more concentrated the solution, the darker the solution would be, darker the solution would be in terms of color, the more absorbance that you would see. Obviously, as it gets to a more colorless sort of color, I guess, it is will have less absorbance value. So using that in Beer's law that we talked about earlier on as well, you could really turn those absorbance values into concentration values, and you could really make a really nice sort of kinetics plot of how something is changing over time, the concentration. A lot of times that's very much helped out these days by some computer technologies. Literally, you could have sensors that can basically take absorbance values every second, which obviously you as a person probably couldn't do that, but be able to read it pretty much every second and really build yourself out a pretty well defined sort of kinetics plot of what is going on. Any questions on any of that stuff there that we talked about last time? Okay. So I think this is about where we left off, and we're sort of talking a little bit about, again, sort of this kinetics idea. And we can see that when we look at we're looking at, say, that BR2 experiment from last time. And again, we do see that as time is changing, we do see sort of the instantaneous rate over those periods of time is pretty variable. And again, that's sort of a snapshot window. But there is really a relationship that does show sort of a constant value, if you will, for a reaction. And that's what's referred to as the rate constant with this guy right here. So this is the rate constant. And as we can see for this reaction, pretty much the rate constant is, as it implies, pretty constant. Sort of gives us an idea how fast the reaction is taking place. The rate constant is little k, and it's an important distinction. Little k here is the rate constant. And that's not to be confused with the majority of what you'll talk about when you go to 200B, which is capital K, which is the equilibrium constant. I'll draw it really big for representation purposes. So this guy you'll deal a lot with in 200B, but when we talk about little k, it is the rate constant. It usually involves kinetics, and you'll probably learn the relationship between these two things as well, maybe next semester. But little k is sort of what we deal with, and it's really a relationship that kind of describes sort of the rate and how fast the reaction is going. So usually sort of the larger value for your rate constant means the reaction is taking place a lot faster. It's kind of the lower value that you have for your rate constant, kind of the slower the reaction is taking place. The rate is proportional in this particular experiment to that BR2. Again, that BR2 was sort of what was reactant. It was a reaction. And remember that, I think it's on the previous page. Yeah, so this is the reaction we're really still talking about in this example. And again, that BR2 is the reactant. So we would expect that this guy's concentration would start to decrease with time, allowing these guys' concentrations to increase with time. And a reminder that, again, this has sort of a color to it. These guys on this side was colorless. So again, following those absorbance values over time allows us really to see sort of what's happening in terms of the concentration over time. That allows us to write something like this, which, as we will see in this chapter here, this is what is referred to as a rate law. And as the rate is equal to K times concentration of BR2. If we rearrange and solve for K, which is our rate constant, we get the rate over the concentration of BR2, and that equals our rate constant. As we can see, ends up being a fairly constant number over the entire sort of reaction here as well. Now, rate constant is really important in addition to sort of giving us an idea sort of how fast or slow a reaction is taking place. There's a lot of really big information that are important information that you could kind of get from the rate law, the rate constant. And that actually revolves around its units. And for example, in this case, these are reciprocal seconds. And as we will talk about in this chapter, just knowing the units that are associated with a rate constant will tell you sort of what type of reaction is taking place. For example, reciprocal seconds tells us that this reaction is first order overall, and we'll talk about what that means a little bit later on. So the rate constant is really important, again, not just necessarily for the sort of information in regards to how fast or slow a reaction is taking place, but it also can kind of tell you, you know, the type of reaction that you're dealing with just solely based off of the units that you see associated with that rate constant. Now, what happens when we have a reaction that maybe doesn't produce any type of color? You know, how can we sort of figure out what is going on in terms of, you know, the rate and how things are changing? And for example, in this reaction here, this is hydrogen peroxide that's breaking down into water and oxygen gas, and this is a gas. These are all really colorless sort of solutions and such, which means if we try to use something like spectrophotometry, like in the BR2 sort of experiment, it really would be useless because there's no color. No color means there's no absorbance. So you're just going to basically be flatlined all the way through in terms of your absorbance values. You're not going to really get any type of absorbance values. But it is a gas, which means we can use something like PV equals nRT to sort of help us out. And it got a little messed up here, so let me just gonna fix that there. I think it's okay on your notes. But basically, P is equal to N over V RT. And as we talked about a number of times with sort of our gases, N over V, that is moles over liters, and that is molarity, which is basically what the concentration is here. So that is going to allow you to figure out the concentration, because again, if we sort of look at this, you probably ran this experiment at the same temperature. And again, R is a constant, which means, you know, you could really figure out sort of the molarity of something by simply following the change in pressure. So if we really solve for that, bring it to the other side, you get molarity is equal to P over RT. So again, really the pressure is kind of the only thing that you would have to monitor in a case like this. As what is being shown here, again, this reaction generates sort of colorless gas. I think they just put some color in there so you can see something in the flask. As it goes through here, this has mercury in it, obviously, and we can measure the change in the mercury, which is obviously the pressure. And that means over a period of time, monitoring the pressure in a reaction like this will give us essentially the change in the concentration of O2 over the change in time. Because in this particular reaction, the only gas present is oxygen. It's a product, which means the only time we're going to get pressure is as this product starts to form. And obviously, as we see a rise in the pressure, that means we have more products. More products means that this reaction has proceeded to the right-hand side. So again, this is another way that you can sort of follow the kinetics of a reaction when you're not dealing with something that perhaps has any type of color and spectrophotometry that you could use. Again, you can do some following of pressure, which is relatively easy, and you can basically relate it back to how the concentration of that gas is changing with time. We would expect, obviously, the concentration of O2 to be increasing with time. So this brings us to sort of what's happening in terms of rates. And obviously, when we have reactions, we do have to take into account the stoichiometry. And that's really important, right? To get sort of that mole to mole relationship. So when we look at something like this, we do see like normal stoichiometry that for every 2 moles of A, we are producing 1 mole of B. So it's really a kind of 2 mole of A gives us 1 mole of B. Again, that's obviously our coefficients here and our stoichiometry relationship. And you do have to take into account stoichiometry when we kind of deal with rates and how they're changing. And we could write what is sometimes referred to as a rate expression. And in this case, the rate would equal, and this is minus, so I'll make it over here closer so you can see it, minus 1 over 2, the change in the concentration of A over the change in time. Again, we see a negative here because it's a reactant. and the concentration should be decreasing with time. Change in concentration of A is basically final concentration of A minus initial concentration. Obviously, change in T, which is again here time, not temperature, is the final time minus the initial time. That equals on our product side, the rate is equal to change the concentration of A. I'm sorry, change the concentration of B over the change in time. On our product side, as we talked about last time as well, it is positive here, again, because the concentration of B should be increasing with time. So again, remember that as we, I think, talked about last time, when we solve for something like the rate of a reaction should usually be a positive number. So when you solve for that rate, it should usually be a positive number. That means that we can, for general equation like this, basically set them all equal to each other. We could say that the average rate of the reaction is equal to, again, it's kind of small there. I'll make it bigger, minus 1 over the coefficient, change the concentration of A over change in time. That also equals minus 1 over B, change the concentration of B over time. Now we're going to our product side, so positive here, no negative. 1 over the concentration, I'm sorry, 1 over the coefficient, change the concentration C over time, 1 over D, change the concentration D over time. This is again what is referred to as a rate expression. This again should end up being a positive number. And I think we talked about it last time, sort of why we have those negatives there. It's really to turn those into a positive number. Again, a reminder that, if we were just making up numbers and this was 4 molar to start with and 0 molar to end with, and this was 2 molar and 2 molar at the end of the reaction, when we take A and we do the change in the concentration of A, it would be our final, which in this case would be 2 molar minus 4 molar. And when we do that, it gives us minus 2 molar. That minus, along with the minus here, turns it into a positive rate. Again, we don't need that on the product side because when we do the change in the concentration of B, that is final, which is 2 molar minus 0 molar, ends up giving us a positive 2 molar to begin with. So it's ready is going to turn it into a positive number. So again, that's why the negatives are important for our reactant side. Again, going to turn our average rate for the reaction into a positive number. Now, when we're talking the average rate of reaction, again, should be a positive number. If we're talking specifically how, say, the concentration of A is changing with time, that can definitely be a negative number and should be a negative number to indicate that it is decreasing with time. Any questions on that? The nice thing about the rate expression is it really does give you a way to figure out pretty much how everyone is changing in a particular reaction. You pretty much just need one piece of information. Either you need what the average rate is, you need to know how a reactant is changing with time, or how a product is changing with time. And from that one piece of information, you basically could figure out how the reactants are changing, the products are changing, everybody's changing by using this rate expression. So why don't you try one here? Why don't you take this reaction here and write the rate expression for this particular one? Okay, so let's take a look here and see how we're doing. So we want to write the rate expression. So here we would take the rate is equal to 1 over the coefficient here. So the coefficient here is 1. So that basically would be 1 over 1. It is a reactant, so it should be negative, the change in concentration of methane over the change in time. Again, the coefficient basically 1 over 1. So you don't really have to put it because it is 1. We could do the same thing for our O2, which is also a reactant. So we would expect it to be decreasing with time. So it would be minus 1 over 2, change in the concentration of O2 over the change in time. That 1 over the coefficient here, 2, again, coming from the coefficient, And when we actually do some calculations with this really does take the stoichiometry part of it into account. So that's really why we're doing 1 over the coefficient. It gives you really the right sort of multimole relationship that's happening. We could also do that to our product side here, but since it's our products and it should be increasing with time, we would expect it to be a positive, and that would then also be 1 over the coefficient, which is also still 1. So this would just be the change in the concentration of CO2 over the change in time, and that equals 1 over 2 again for the coefficient, change in the concentration of water over the change in time. This is the way you could write the rate expression. By the way, since these are all these guys are equal to basically the same rate, the same average rate of the overall reaction, that means you could write it all like this. You could also individually just pull out pieces that you need. You could say, hey, this guy, and you could also go, the rate is equal to minus 1 over 2, change in concentration of O2 over the change in time, where this number and this number would be the same. So that's what allows us to sometimes solve for something by using that relationship, again, with the 1 over the 2, taking the stoichiometry into account, all in the same calculation. If you want, and it may not make sense right now, but if you wanted to, and we'll see maybe an example of this in just a second, you could just do a stoichiometry problem first and then do the kind of the kinetics part of it second. But doing the 1 over the coefficient kind of wraps both of those calculations together, both the sort of kinetics part of it and also the stoichiometry part in the same step. Any questions on that particular one there? All right, so why don't we try one actually with some numbers here and see what you come up with. Why don't you, for the reaction given, if the concentration of I changes from 1 molar to 0.868 in the first 10 seconds, calculate the average rate in the first 10 seconds and the change in concentration of delta, change in concentration H plus over the change in time, basically. That's what we're looking for. So we're really looking for that there, change concentration of H plus over the change in time. All right, why don't you take a second or two and see what you come up with. Okay, let's take a look here. So let's just pull out sort of the information, see how to approach this guy here. So for the given reaction, we have the concentration of I minus goes from 1 molar to 0.868. So really we have the kind of the initial concentration here of I minus, initial, and that is 1 molar, to our final concentration of I minus, which is 0.868. That makes sense to us because it is a reactant, so we would expect concentration to be going down. So we do see that sort of decreasing, and basically our time here is 10 seconds. So we're got information about I minus, and we're interested in H plus. So what we want to do is basically find our rate expression relationship for these guys. So we know that the rate is equal to minus 1 over 3 change in concentration of I minus divided by the change in time. Again, minus because it's a reactant, 1 over the coefficient, going to take into our account the stoichiometry part of that. And we do have all this information, so we really can plug it into here. So this would be minus 1 over 3. We would do our change in concentration of I minus. So remember that is final minus initial. So 0.868 minus 1 molar. That part is important because, again, this part is going to give us a negative number. Along with the negative that's here, we'll turn our rate into a positive number, which again is what we're aiming for here. It was a total of 10 seconds, so you could really go final, which is 10, minus initial, which is 0 seconds. And now if we do that, we will end up with 0.868 minus 1 divided by 10 divided by 3. Again, the 3 is important there. That's going to take the stoichiometry into account, and that gives us a 0.20, it looks like. 44. Now the units here do not cancel, so molarity is up on top per second, and that is a average rate for the reaction of 0.0044 molarity per second. Again, we end up with a positive number because we did our final minus initial for our reactants, so negative and negative, again turning that into a positive number. Any questions on that there? Now, that's not the complete answer. That is just this part of it. That is the average rate. The other thing that we're interested in is really how the H plus concentration is changing with time. So what we can do is now just take the relationship that we could get from the equation about H plus, and we see that the rate is equal to, again, minus, because it's a reactant, 1/2 for the coefficient for H plus, the change in the concentration of H plus over the change in time. So now what we're really looking at is the rate that we just calculated here is the same rate that would be here. So we have that number from above. And what we're really looking to solve for in this particular case is this whole thing. So we're looking to solve for really this whole thing here. So this is a very common mistake sometimes people make, is they divide when they should multiply, multiply when they should divide. Again, by doing this, you could hopefully see that what we really need to do is multiply the 2 to the other side. But it's not just the 2, it is also the negative needs to come to the other side. So really what we need to do is go negative 2 times the rate would equal the change in the concentration of H plus over the change in time. We have all these numbers, so negative 2 and 0.0044 molar seconds is equal to the change in the concentration of H plus over the change in time. That finally gives us a negative 0.0088 molar seconds is how our change in concentration of H plus over the change in time. Any questions on that particular one? So a couple important things here just to note, as we were talking about earlier, maybe this will help sort of it sink in a little bit. As I mentioned before, the average rate of the reaction, which is this guy here, should always be a positive number. But when you're specifically talking about sort of the rate or how a particular reactant is changing, it actually does need the negative, because this negative indicates that the concentration is changing in the downward way there, decreasing with time. Any questions on that calculation there? Okay, why don't you try another one here, see what you come up with. So we have 2.4 times 10 to the 2 grams of NOBR. That is the molar mass, grams per mole from the periodic table. Decomposes in a 2 times 10 to the 2 flask in 5 minutes. Calculate the average rate of BR2 production and molarity per second. So see what you come up with, and we'll talk about it. Again, approach it kind of the same way as we just did the previous one here. Let's take a look at this one here. So again, we're interested in BR2 production, and we're given information about NOBR. So we'll start with the NOBR, since that's the information we're sort of given. So again, we could write the rate expression here from the equation. The rate would equal minus 1/2, again, because it's a reactant, change in the concentration of NOBR over the change in time. At this particular case, we have that it decomposes moles and our grams and milliliters. From that, we could get molarity, and we also have 5 minutes, which is a unit of time. So really, we could get the change in molarity here by taking really moles per liter. We do need to get us into moles here, so we do need to do a conversion. We have the molar mass from the periodic table. So the moles of NOBR would equal 2.4 times 10 to the 2 grams of NOBR using the molar mass again if it was not given to you from the periodic table there, and we get 109.91 grams per mole. That gets us 2.4 to the 2 divided by 109.91 gives us 2.18 moles of NOBR. Remember, though, that this is molarity, so we do need liters. This is basically 200 milliliters, which if we convert it is 0.2 liters divided by 1,000. So we could actually then figure out the change in molarity, which would be 2.18 moles divided by 0.2 liters gives us 10.92 molar. And again, that technically would be what number we have here. Now, we could put that in, but we also need on the bottom the change in time. So it told us it was 5 minutes. Since ultimately we're looking for seconds here, at some point we do need to do a conversion between minutes to seconds. So we will take our 5 minutes and convert it into seconds now, just so it's out of the way and it's in the right unit. So in 1 minute, there are 60 seconds. So that's going to get us, was that 300 seconds, I believe. And now we have sort of the seconds part. We have this part. We now can basically plug it in to get the rate is equal to -1/2. Now our change in our concentration of our NOBR is 10.92 molar. This is actually, even though it doesn't say it kind of anywhere, we need to be careful of signs. This actually should be a negative number. And it should be a negative number. As we talked about, this is a reactant, which means when we do kind of our final minus our initial concentrations, we should end up with a negative number, which is essentially where the 10.92 would have came from, and it should have been changed negatively. Again, that way the negative and negative here will give us a positive value for the average rate here that's going on. So negative, and then our 300 seconds on the bottom, and that will tell us that we will end up with here 0.0182 molar seconds as the average rate. Any questions so far on that calculation? And again, I'll explain why that's important, that sort of negative thing that we just did there, and why it really will sort of mess up your answer if you are not careful of it. And it's because this answer right here is technically maybe not the answer that we're looking for, because remember, this is the average rate of the reaction. We're actually looking for BR2. So we then want to look at what is the relationship between the rate and BR2 production. So the rate in this case would be 1 over the coefficient, which is 1, the change in the concentration of BR2 over the change in time, which basically means the number we just got is the rate. So that means that the change in the concentration of BR2 over the change in time, how it's changing, is also 0.0182 molar seconds. And that actually is the answer here to the question. And it is a positive number here. And that positive number does make sense because it is a product. So we would expect it again to be increasing with time and positive. So that's why this negative here is really important, because if you did not put that negative there, you would have found yourself with a negative rate here. And when you would have put it into the answer here, you would end up getting a negative rate for how BR2 is basically changing with time. And that would not make sense again here because BR2 is a product, so it should be increasing with time, which is a positive number. And if you did not take care of that negative earlier, you would have showed it actually, as you're making products, the concentration going down, which again would not make sense. So these slight little things, you got to really kind of be careful, kind of think about, are you dealing with the reactant? Are you dealing with the product? Again, if you're talking about how a specific individual reactant is changing with time, like we did on the previous problem, you do need a negative at the end. If you're talking about how a product is changing with time, like we're doing here, you do need it to be positive at the end. And if you're talking about the overall sort of average rate for the reaction, that should be a positive number as well. Any questions sort of on that calculation or this type of calculation here? Now, earlier I spoke about that, we do the 1 over the coefficient for the stoichiometry, and to take care of the stoichiometry, you could, as I mentioned before, really do this problem as kind of like a regular stoichiometry problem to begin with, and then sort of put in the sort of kinetics aspect of it. And what I mean by that is, we're really interested in BR2 here, right? And we got information about the NOBR. So we could do the mole-to-mole relationship here and say, as we normally would in like a stoichiometry problem, there's 2 moles of NOBR is equal to 1 mole of BR2. And we could have picked up this calculation right here and kind of just did the stoichiometry part first, 2.18 moles of NOBR, and just did a basic stoichiometry problem to get us over to BR2, 2 moles of NOBR, 1 mole of BR2, and we would have ended up with 2.18 divided by 2, 1.09 moles of BR2. At that point, we could have then divided by our 0.2 liters of, it was divided by 0.2 liters, gives us 5.45 molar. We then could have divided by the time, which was 300 seconds. And we would divide that by 300. We end up with 0.0182 molar seconds. And again, this would be for our BR2. So you can see you can do basically just a straight stoichiometry problem and then kind of do the kinetics aspect of it or the rate aspect of it by dividing by the time, and you end up with the same thing. And this is why when we talk about going 1 over the coefficient, like we did here, right? 1 over the coefficient. That's because if you look at what we're really doing, that's 1 over coefficient right there. It's the mole-to-mole relationship. And again, that is what the kind of 1 over coefficient does for you. It kind of does it all in one sort of calculation, if you will. But you could just as easily sort of do sort of first the stoichiometry problem, followed by sort of the kinetics aspect of it. Any questions sort of on rate expressions? So again, we do use rate expressions to help us determine what's going on with everybody, reactants, products, and so forth. Any questions on that there? All right, so we're going to now talk a little bit about some of the factors that affect rate. And we're going to go into a little bit more detail in some of these, obviously, as we go through the rest of these chapters. So sort of a kind of a preview little slide here. But really the nature of the reactants really does play a pretty big effect on sort of the rate of a reaction. Typically speaking, smaller molecules tend to react faster than larger ones. Gases react faster than liquids that react faster than solids. Think about gases, they're flying around, so they're constantly in motion, they constantly have energy, which means they're pretty much good to go to react. Liquids as well, a little bit more movement, so good to go. Solids are just kind of sitting there, so they're kind of slower to react. When we talk about solids, some solids are more reactive than others. So things that are powdered solids are more reactive than block solids. Again, greater surface area, so greater areas, more areas of contact where reactions can take place. So that usually indicates that it will react faster. We also talked about sort of reactivity of metals. And ions are really help in terms of sort of the rate of reaction. Again, if you think about ions, they're typically in solution, they're floating around, they're kind of good to go at that point. Temperature, as we will see, is also a really important thing that affects sort of the rate of a reaction. And typically, if we increase the temperature, the rate of the reaction will also increase, and vice versa. If you kind of lower the temperature, typically speaking, the reaction rate will decrease as well. On average, if you go about 10 degrees higher in temperature, you typically, in a lot of reactions, will double the sort of rate of that reaction. If you just think about temperature, as we'll talk about, when you increase the temperature, everybody has more energy, everybody's moving faster. It allows sort of that process of reactions to sort of occur a lot faster. Vice versa, if you kind of lower the temperature, everybody has a lot less energy, they're not moving around as fast, reactions tend to kind of slow up. There's the Arrhenius equation, which we'll talk about a little bit later on, which basically describes that relationship between sort of the rate and the temperature that we will see. Other important things are catalysts. Catalysts, as I think we might have touched upon sometime here, but just a reminder, catalysts are not a reactant. They're not a product, and they don't get used up in a reaction. They really are there just in most cases to facilitate the reaction occurring faster, to speed up a chemical reaction. There are actually catalysts that slow down a reaction, but in most cases, if somebody is speaking about a catalyst, they're probably talking about it in the case of it speeding up a chemical reaction. A lot of times we see catalysts laid on top of the arrows, so like platinum, some type of metal. Sometimes you'll see H+, which means it's like an acid sort of environment or catalyst here. As we'll talk about towards the end of the chapter here, catalysts can be homogeneous, which means they're in the same phase as everybody that's reacting. They can be heterogeneous, which means that they are in different phases than what is reactant. But ultimately, a catalyst just sort of works by a lot of times sort of providing a place where everybody could kind of come together a little bit more efficiently and start reacting more efficiently than if the catalyst wasn't there. They're just going to be moving around trying to find each other. Everybody's sort of attracted to a centralized location, and that oftentimes will allow the reaction to proceed a lot faster than, again, them just kind of floating around trying to find one another. The concentration is really important. The larger the concentration of reactant molecules, usually the faster the reaction will be. So if we think about molarity, that is moles of solute per liter of solution. And remember that it really is the solute here that's reacting. It's really the thing that is reacting, which means if I have a really big concentration, large concentration, that means that my moles are very large on top, right? Large number divided by a small number gives me a larger number, right? So that would mean I have a lot of moles, and basically what that means is in the solution, I got a lot of guys in there ready to go, ready to react, and we would expect, again, the reaction to occur a lot faster. Gases depends on partial pressures. The higher the pressure, the higher the concentration. Again, if we just think about our gas relationship, higher pressure, lower volume, which means, again, all of our gas molecules are pretty much right near each other, which means there's probably going to be an increase in collisions. Increase in collisions means we're going to have an increase in reactions, and thus the reaction rate will probably happen a lot faster. And again, that concentration of our solutions depends on, depends on the molarity. And again, the greater the molarity, the larger the solute sort of concentration is in there. Any questions on that there? And again, we're going to talk about some of these things a little bit more detail for the rest of this chapter. But for now, I think it's probably a good stopping place before we get into